So why do we still not allow our machine learning models to make medical decisions? There's a very practical reason for this, and that is that the healthcare data itself does not conform to the requirements of the machine learning. So in hospitals, the data is gathered to make diagnosis or treatment plans, and the machine learning task is to make predictions from the data. It's fundamentally a different task. So there's a misalignment between the expectations here. And even if we make predictions, these predictions oftentimes are not useful for the clinicians. They will say, well, we can't use this. This is not clinically relevant. So I want to bridge this gap by clearing these misunderstandings between the data scientist and the medical expert. And I will show you that it is possible to build machine learning models with the medical data through working together. So this presentation is structured as follows. First, I will talk about the medical data, how it is not the same as machine learning data, then how the medical data inherently has certain limits, and how the standard machine learning tasks in data science is not clinically relevant. So medical data is not the same as machine learning data because it is formatted differently. Picture the scenario where a patient goes on a consultation with his doctor at a hospital, and then the doctor makes an inspection on this patient to put together a diagnosis or a treatment plan. So we have three different kinds of data we get from this. We have the patient information, which is static in nature. We have the point in time of the visit, which is a longitudinal data modality. And then we have the forms with the measurements, which are hierarchical typically. So this is not very convenient for a machine learning model. What we want is tabular data. So for the psoriasis dataset, for example, we have these tabular data where each row is a visit of a patient. So we have the patient information, and we also have the forms with the measurements, like the psoriasis information and the comorbidities and such. And then once we have this tabular data, we can put on top of this machine learning model, like illustrated here with a tree-like model. So we have now a convenient format for our data, but we still haven't looked at our data yet. And this is also very important because we find some limits here. The first of which is that there's a lot of missing data in the healthcare data. For the psoriasis datasets, we have here 3 medication types of the biologic medication. And in total, we have 195 features for this. But on average, for the worst medication type for data quality, we have 72 missing values. This is a lot of missing values. So we want to try to fill in these missing values. The first thing you can do is ask your hospital or your medical expert if they have information in patient records. Typically, as data scientists, you won't have access to this, but you can ask regardless, and maybe they may be able to grant you some new information. Then another thing that you can do is imputing or predicting the missing values. It's a medical use case, so you should be very careful about this. The decisions that you make here have real-life consequences, so always ask your expert if you should impute this and how you should impute these variables. An example shown here is of the weight of the patient. This is a very simple task. There's a lot of variability in the weight throughout time, so it's quite safe to predict this type of data. Then another thing in the data that can be found is structured missingness. In the psoriasis dataset, the information is collected through answer and question format. So a patient can be asked if he smokes a lot, and the question is if he smokes, yes or no. But if he answers no, it doesn't get presented the question of how many times in a day that he smokes. So this is a missing data field. But thinking logically about this, we can merge these two questions together. We can just fill in the number of 0 for the amount of times in a day that he smokes. So then we reduce the amount of features and we eliminate the missing data field. Then we can also look at the quality of the data, of how many missings there are in each row and each column. For example, in the clinical study, it was found that the measurement of the hemoglobin was not relevant anymore. And from that point onwards, it was not measured anymore. So from that point onwards, these are all missing values in your data. But because it was not relevant for the clinical study, it may also not be relevant for your data science. And as such, you can consult your experts, and indeed, you can drop this feature, for example. Then there can also be patients that don't show up to their visits. They are underrepresented in the data, there's little information on them, and even if these visits happen, they may have a bad quality because there's not a lot of information noted down. So you may consider dropping in this information as well. Now, this is a list of things you can do. This is not comprehensive. Depending on your data sets and the characteristics of it, there are a lot of things you can also try, oftentimes found in literature as well. Now, another aspect of medical data is that there is little data. In this case, for psoriasis datasets, we have 195 features for 842 visits across 194 patients. So there's a lot of features for the amount of visits we have, and machine learning models will tend to overfit on these problems. So we should consider this when we select our machine learning model, and we should also consider that we have missing data. So we can use, for example, then the XGBoost or the GetBoost models. Another thing you can do for handling little data is feature selection methods. So they reduce the amount of features you use, reducing the complexity of the problem and also reducing the tendency to overfit on the task. The third problem within medical data is that the data distribution is unbalanced. For example, here we see the PASI score, the disease severity, and the amount of times it occurs in the data set. So you see that there are a lot of visits with PASI scores between 0 and 2, and that is because patients come back to the hospital when they already have taken a medication and the clearance rate is higher of the psoriasis. So they have an improvement in comparison to the last time. And because of this, the very severe PASI scores are less frequent in the data. How can we force our model to look at also these rare examples and learn from this? So some examples that you can input is oversampling. So you can duplicate your minority examples so that it occurs more in the data and that the model can learn from this. But you should be very cautious of this because it increases the tendency to overfit. Then you can also assign weights to your examples so that there is more focus placed on these rare examples. Now, we also want to have a good evaluation of our model. And we also want to know if we fail at predicting these rare examples. So for that, we can adjust our training scheme with a leave one patient out cross-validation. So we train on all patients except one, and then we test on that one patient that is left out. And we do this for every patient. And in that case, we can see where our model fails and where our model succeeds. And then we can give a reliable estimate of the performance of our model for these rare examples. So now we have our machine learning pipeline designed, but which tasks do we predict? Now, a typical standard machine learning task in data science is not always clinically relevant. There can be a couple of reasons for this, and it's, for example, an irrelevant prediction time frame. So suppose you have data for 2 years or more, and you make predictions for all these 2 years, and you present the evaluation on this to the hospital. They will say, well, we don't find this really useful because we only look at the first 3 months of predictions because we want to know if we want to switch to this medication that's in the data set. So the evaluation should only happen on these first 3 months in that case. Should we throw away all of the other data then? Well, no, we already have little data, so it can be better to train on all data. You should try it at least to do this and see how many data is useful. Then a standard machine learning task that we can do is the regression of the PASI score. So this is without any operations on the labels and such. So we have a regression with a mean absolute error of 1.3 and with a standard deviation that's quite high of 1.8. And we present these results to the hospital, but they say, well, we don't really care if the PASI score is higher than 5, because we want to know if we want to use this medication where there are predictions made for. And if the threshold is exceeded, the PASI score of 5 is exceeded, then we won't use this medication. So it doesn't matter if the PASI score is 5 or 6 or 7. So our labels are not really significant for the clinical task. So we have to transform our label space in this case. We can do this with binning or clipping, or we can also do a transformation with a log transform or power transform, so that the clinically relevant part is more in view of the machine learning model. We can also redefine our machine learning task, and we can do an ordinal classification, and we can predict if the disease will be mild, moderate, or severe. Or altogether, you can just choose another clinically relevant evaluation metric that is useful for the hospital. Now, for example, what we did, we clipped the label to a maximum of PASI 5. So the model can't see any PASI scores above the threshold of 5, and it will redirect more of its focus towards the region between 0 and 5. And we see that the mean absolute error is actually reduced by a factor of 2 because of this. So I showed you that medical data is not the same as machine data because it's formatted in a different way, and we want the wide format tabular data for this. The medical data has also its limits. There's little data, there's missing data, there's an unbalanced data distribution. So we should take this into account and try to solve these aspects of our data. And the standard machining tasks in data science are typically not clinically relevant. So always align these expectations with your hospital, for example, the prediction time frame or the label significance. So I've showed you that we can build machine learning models by working together with a medical expert. Incorporating their medical expertise can help us to clean the data, to build a machine learning pipeline, and to align the machine learning tasks. So although the quality of medical data is far from perfect for the data science, each improvement that we make on our machine learning pipeline increases the usability of our machine learning models. Thank you.